Okay, so let's have a look now at the intensity of light on a screen in Young's double slit experiment. First thing you're going to notice is when you look at the interference pattern of the double slit experiment is that they're not very sharp edges. There's actually a little bit of blurring. And so the intensity that we're going to be calculating in this lecture is going to be the intensity at the center of the fringe. So what we're going to be calculating today is the distribution of light intensity associated with the double slit experiment. So there's three main assumptions that we're going to make when we do these calculations. Firstly, that the two slits represent two coherent sources of light. And that brings us to our next assumption, which is that the waves have a constant phase difference. So remember, the phase difference isn't changing. For it to be coherent, they have to have the same phase difference. Also, we are assuming that the waves have the same angular frequency. So therefore, when we're looking at the interference pattern, remember we have constructive interference where there are bright fringes and destructive interference where there are dark fringes. Therefore, the total magnitude of the electric field at any point on the screen is going to be the superposition of the light rays coming from the two slits. So if the total electric field at a point on the screen is the superposition of two waves, what we can do is write an equation for both of those waves. Now, remember our equation for our electric fields, you'll remember from before, from an earlier lecture, is E equals E naught or E max, which is our amplitude, sine omega t. So we're going to have two of these equations, but one has to have a phase difference, remember? So we'll have E1 equals E naught sine omega t, and then E2 equals E naught sine omega t plus phi, where phi is the phase difference, and that phase difference isn't going to be changing. Now, this phase difference isn't going to be changing between these two waves, but the phase difference is dependent upon the path difference. So for a particular point on the screen, the phase difference isn't going to be changing. But if we move to a different point in the screen, then the phase difference is different from that initial position, wherever we were. So for example, take the middle point in the screen where the rays of light have traveled the same distance, the phase difference or phi is going to be 0. And that's going to be different if we go to different points, different vertical points on the screen. Therefore, for different points in the screen, we need to calculate the phase difference explicitly. So for one adjacent bright fringe away from the central bright fringe, remember the path length difference between the two rays reaching that point is going to be one wavelength. Therefore, the phase difference at that point is going to be 2 pi. So you can see a bit of a pattern going on here. What we want is what is a general phase difference? So we know that the phase difference is going to depend upon the path difference. So remember, for a path difference that is one wavelength, the phase difference is 2 pi. So what we can say is that for some fraction of the wavelength, so for example, delta L divided by lambda, what we get is phi divided by 2 pi. So we have some fraction of the wavelength gives us some fraction of a phase. So the path difference between two points on the screen is going to be given by, remember, our d sine theta. So we have delta L divided by lambda equals phi divided by 2 pi. Therefore, we get phi equals 2 pi divided by lambda multiplied by delta L. We shove our delta L in from before, and we end up with 2 pi divided by lambda d sine theta, and that equals our generalized phase difference. So now we have a generalized phase difference. Let's work out what the magnitude of the resultant wave is going to be on the screen. So remember, the magnitude is the superposition of the two waves. So we have our two waves from before, E1 and E2. Therefore, the total is going to be E1 plus E2. So when we add them together, we're going to have E naught sine omega t plus sine omega t plus phi. And so remember, to combine these two together, we end up with E equals 2 E naught cos phi divided by 2 sine omega t plus phi divided by 2. So remember, way back when we started this optics topic, is we worked out that the intensity is related to the square of the magnitude of the electric field, and that's what we're going to be using to work out the intensity. So then to work out the intensity, what we can do is we can say I divided by I naught equals E squared divided by E naught squared. Now this E naught is the amplitude of the electric field of one of the waves. Remember from before, our equation was E1 equals E naught sine omega t. So E naught is the magnitude of the electric field for one wave. So I naught is the intensity on the screen when one of the from only the contribution from only one of the slits. When one of the slits is covered, it's the intensity from the other slit, and therefore I is the intensity for both slits, and E is the magnitude of the electric field when we have both of our slits open or uncovered. So using our equation from before for our E value and then squaring it as we're about to do here, what we end up with is 4I naught cos squared a half phi. And that is our intensity I. So then the question is, well, what is half phi? Well, remember from before, we got an equation for phi. This is our phase difference that changes as we move up and down the screen. So we have an equation for that. So our equation for phi, remember, was our 2 pi divided by lambda d sine theta. So we can sub that straight back in, and what we end up with is I equals I max. Now I max is going to be 4I naught cos squared pi d sine theta divided by lambda. This is a good equation, except the sine theta is looking a bit messy. So we can actually approximate our sine theta from before. Remember how we had our entire setup and we could say that theta is roughly equal to y divided by capital D, which D being the distance from the slits to the screen. So what we can say then is if that is roughly equal to theta, and for small angles, remember this has to be for small angles, we can say sine theta is roughly equal to theta. Therefore, let's put that y divided by d into our equation. And what we end up with is I equals I max cos squared pi d divided by lambda d multiplied by y. So an interesting conclusion that we can make from this intensity equation is that the distance d between the slits in the screen is usually much, much, much greater than the distance between the two slits. For small angles, so therefore small values of y, and for d being the distance between the slits being much greater than d, the separation of the slits, what we end up with is that the interference pattern on the screen consists of equally spaced fringes that are roughly of equal intensity. And if we look at the plot that I've got here on the screen, we can see that we've got maxima and minima. So we have, for example, we start at 0, and then if we look at the top row, we have 1, which is our next central bright maxima, and then we have 1, which is our next maxima, our first order maxima, either side of the central one, and then we have 2, which is at 4 pi, and that's our second order maxima. And similarly for our minima, we have our first minima at pi, a phase difference of pi, and then for the first order minima, we have the phase difference at 3 pi, etc. And then down the bottom row, we can see we have our path length difference as a fraction of the wavelength. So for example, at the first maxima, remember we said there must be a path length difference of 1 lambda or 1 wavelength, and we can see that that's what delta L divided by lambda is. And that's the intensity distribution in Young's double slit experiment.